by Mike Ford, who was until recently PhD student, and unfortunately couldn't make it, although he paid the conference fee. Fortunately, didn't pay for travel before realizing that he couldn't come. Okay, so, and he works for this company who sponsored his PhD, Jivkov. I'm first going to talk about, this is about local approaches to cleavage fracture, which is a topic that has been slightly abandoned by a lot of people around the world, although it's not solved at all. So I'm going to talk about the basis for current local approaches and the micromechanical approach that Mike Ford developed to test this basis, because we are not happy with that, with the basis, and then some results from the model and some conclusions. So the conventional local approaches for cleavage fracture, they start with the assumption that cleavage fracture is a Poisson process, which means these three things. The probability of failure of elementary volume, like these many things here, is proportional to the volume. The second thing is that the probability of more than one failure in one elementary volume is close to zero, is taken to be zero, which is the weakest link assumption. And the third one is that the failure events in these joint volumes are statistically independent. So when you take these three assumptions of the Poisson's process, you build all the local approaches to cleavage fracture. And from there, the logic continues like that. You have second phase particles, which are initiators for damage. And some of them, not all of them, form microcracks. And then the local approaches say like that, well, the microcracks, the microcrack density curve is something that we don't know. We do know the density of particles that can be measured experimentally, but we don't know the microcrack density. And therefore, we assume that it looks like a power law. And then the shape of that power law is calibrated with experiments. Okay, but when you calibrate with at one temperature and one constraint condition, and you want to move to another to predict probability of failure at another temperature, another constraint condition, or irradiated condition, you fail. So essentially, this is the distribution of microcrack density, and there is a critical microcrack size, and then you say if there is a critical microcrack size, critical microcrack in your structure, then it can propagate. So that is the challenge, and it has been the challenge for all the time, although there have been a lot of trials to fix the problem. Eventually, when you calibrate at one temperature and constraint condition, you cannot, in most cases, provide accurate prediction at another temperature or constraint condition or irradiation condition. In a way, if you know how the deformation properties change, you would like to be able to put it in the model and predict how the fracture toughness properties would change. But that's exactly what is not possible. And what we want to know, what we want to develop or to have is a faithful model that accounts for the fact that the model that can capture the particle failure, it should be able to decide whether this failure leads to microcrack formation or a void formation. This is particularly relevant to the ductile to brittle transition regime. It should be able to somehow say what is the size of the defect out of this particle failure. It should be able to account for interaction of voids and cracks. It should be able also to account for the population of initiators, which is a measurable property by metallography, including to account for the fact that there may be a depletion of these particles with the load. And it should be able to say what is the critical microcrack size for propagation. The thing that we think is the problem with the existing local approaches is that all these different factors, although some of them are taken in different models, some in other models, they vary differently with stress strain conditions. That means in different locations ahead of the crack, different factors may have different contributions. And that is questioning the assumption that we have a single microcrack density curve and the entire basis for example, the Berryman model. So what we took to do, or Mike took to do, was to create a micromechanics approach where he models the particle failure by deciding whether it's going to be decohesion, and for that he uses a sort of a Gerson model, or it's going to be ruptured and forming a microcrack. For that he uses a model that the three authors on the first page published in 2014, so it's been 10 years now. Then he wants to be able to follow the competition of ductile damage with cleavage. So particles will be consumed by forming voids or microcracks. Also to predict mechanistically the defect size, to account for interaction between local damage between the defects, so that load is distributed into regions into the region surrounding the defects that form, and the coalescence of defects. And eventually he wants to be able to consider macro crack effects, so that he uses the model at each integration point, for example, separately, and then to scale up representative volumes. And I'm going to show only two simple things out of this, because it's a long story and you'll probably be able to read the details. But the load redistribution he handles in this way. If you have a void that forms, then the excess of stress that happens at the void end is redistributed linearly to certain distance that depends on the void size. This is the horizon. And if there is a defect within the horizon of this defect, not defect, particle within the horizon, then that particle sees the increasing load. And if there is another defect already formed in the horizon, then there can be a coalescence if the condition for coalescence is met. And some example how it works. So this is just one picture that is followed. This is at an integration point ahead of a crack in a 3-point bend specimen. And this is the load here that you see, the stress intensity factor that is increasing. And then you have, I'm sure that there is some word there, which I cannot read now. I think these are the number of voids. These are, sorry. Yeah. These are the increments in the solution. Okay. Number of voids, number of microcracks, aggregate voids that are formed by coalescence, aggregate microcracks, and so on and so forth. And the simulation starts with a distribution, a random distribution. We have 10,000 particles initially. A very small number of those are already voids, because you can see that also in the real material. So there is a certain number of voids initially. And these 10,000 particles are distributed along grain boundaries, triple lines, and inside the grains. What you see here is only the ones that are distributed on grain boundaries and triple lines. The underlying microstructure is not visible because it's going to be too difficult to explain. And so in the beginning, you have these voids here, and this is the picture of everything, the voids and the remaining particles on grain boundaries. So when you start increasing the load, you see the first penny-shaped cracks forming. These are the blue dots here. And some voids are increasing, and then and the first aggregate of two voids. You increase further the load, you see a large further microcracks that are forming or extending, and a large microcrack, which is over here. And at the same load, the next simulation step, this microcrack consumes a neighboring void. You can see here from the reduction of the voids, and becomes a larger microcrack. And this is going on. These lines here show large defects. The reason they are lines like that is because this is a periodic structure. So this point is actually very close to this point on the other side. So it's a little bit confusing. And then you have, so we are here at load, almost the collapse load, just below. And you have very large aggregates on the cusp of collapsing. And just a small increase of the load leads to collapse. And that is the microcrack that is forming the collapse. Okay. You can see that the largest microcrack actually is changing. Yes, I will finish. It's changing with the increase of the load. In the beginning, these were the largest microcracks, and eventually it was the 29th particle, for example, here that failed. So now what we did is we took this model and we used it for all positions. First of all, this was one realization. We did 100 realizations, and the results here are the average of that. So these are the averages of 100 realizations, 100 distributions of particles. So this is the distribution of microcrack density ahead of the crack, perpendicular to the crack plane, and along the crack line. In high constraint geometry, and this is ahead of the crack plane, ahead of the crack in a low constraint geometry. You can see that microcrack density varies with stress strain conditions. And that is contradicting, well, in the existing local approaches, this distribution is constant. You are assuming that the microcrack distribution is exactly the same everywhere. So that is one of the problems. Well, there are models where the microcrack distribution is controlled by plastic strain, but it's like falling like that, like the plastic strain distribution, which means the peak is at zero, and the peak is infinite, in fact, in a elastic plastic material. So this is one of the things that we found with the model. And the second thing is the largest microcracks. The largest microcrack is also varying ahead of the crack, normal to the crack plane and along the crack line. And it's quite differently varying in the low constraint geometry. So the takeaway from here is that the way that plasticity develops has a very strong effect on where you find, or the probability of finding a microcrack capable of propagation. And that means that if you assume a single curve, at some point the curve may be like that, and another point may be like that. It can be changing everywhere. And when you do one single calibration, you may be calibrating this curve, but in a different constraint condition or temperature condition, you need a different calibration. And so the model as it is, the existing models are not transferable. And the last point here is that, yes, I just explained, the tail may vary significantly. So to the conclusions, we have presented this micromechanical model, which can predict the size of the largest microcracks, the number density of microcracks, and the critical microsize crack for propagation. And the idea is that it can be used as a subroutine for either coupled models similar to GTN or decoupled calculations of a probability of cleavage. Thank you very much.